know since you found this information session in the first place. But what I'll go through today is aiming for like a half-hour overview of the types of research that my lab does, geared specifically at prospective students. And then I would really like to have some unstructured question and answer time for all of you to ask questions about research at CU or in my lab. Um, I unfortunately can't really see the chat while I'm showing you the slides, but Megan will be monitoring the chat. And if there's anything that's like questions about the presentation itself, Megan, if you could just unmute and voice those, that would be super awesome. And then we'll do like more general questions at the end. So thank you all for coming. I'm excited to share with you a little bit about the types of research that I do, the types of research that's done in my lab at CU, and why we do this research in particular. And then give a bit of context in terms of what it means to do research at the graduate level and specifically in my lab. So the reason that I research statistical and geospatial machine learning is because I'm excited about the immense potential for machine learning to help us make sense of the vast amount of data that we have that's collected around the world, in particular to help us monitor important environmental, ecological, and social phenomena, and to use this information to make decisions and policies that hopefully benefit everyone. So when I'm thinking about that, I'm thinking about a lot of different data modalities, from satellite imagery to phone data records to census and health records that we have around the world. And thinking about applications ranging from mapping tree canopy height to detecting small-scale metal mining across multiple countries. And the goal here is to use all of this information, translate it into the data-driven insights that can actually help drive policy, help drive information at global scale. But while that picture looks really good, data comes in, machine learning processes it, people use the processed information. It's not guaranteed that using a machine learning algorithm to generate predictions is actually going to result in any sort of benefit, right? So despite the impressive and rapid advancements that the field of machine learning is making, when we use these advancements in algorithms that are developed in the lab, kind of these gray boxed algorithms, we just use those out of the box. They can either exacerbate or introduce harms or unfairness, as we've seen in the news cycles many, many times in the last decade. Or they might just be ineffective at solving real world problems at hand because these algorithms are made for a certain type of data or a certain type of output, but what we need for working in the real world actually looks very different. So in order to achieve benefit, machine learning systems actually need to not just think about this gray box, but think about a much wider, broader context of design and use. And so what my lab does is we think about the types of data that are being input into these machine learning algorithms. We think about the types of uses that their output will have. And we expand the scope of the statistical models and frameworks that we design and analyze. So I'll show you a little bit more specifically what that looks like in two ways. The first part of this talk will look at machine learning specifically for remotely sensed global data. And the second part of the talk will look at the other side of that picture. If we need our predictions to be accurate and to be fair for many different people in our population, can we actually say what that means in terms of the types of data and representation and training data that we might need? And then I'll finish up with some of the future and current directions of the lab in context-driven machine learning. And then at the very end, we'll have a lot of time left over for Q&A, hopefully. So getting into the first part here, machine learning for remotely sensed data. There are currently over 1,000 satellites observing Earth. These are collecting over 90 terabytes of data every single day. And that's a ton of data to think about processing. It is a perfect setting for machine learning to come in and automatically process all of this data. And machine learning and computer vision have been used to help with environmental monitoring at global scale, to helping with real-time disaster response. So after natural disasters, estimating where damage is greatest, estimating where road networks are blocked so that people can send aid to the right places immediately. To even longer term policy and food security, crop yield prediction, and poverty estimates. So really, really real world impactful applications here. So it is really important that we get the methods right, that when we translate satellite imagery into a predicted map, that machine learning model, which is kind of nebulously in this green arrow here, needs to be as good as we can make it, because these are going to be used for really important applications. And so it becomes very important that we develop tailored methods that are accurate, efficient, and accessible with this huge amount of data. But as it currently stands, working with satellite imagery and computer vision is really expensive. It comes with computational costs, like needing GPUs and tons of storage for the imagery, as well as costly in terms of needing that machine learning expertise. And as a result, many of the solutions end up being quite domain specific. So you might design one specific model that's trained to generate one type of prediction. Here you see a prediction of global population density. But when we step back and think about it, this one satellite image actually tells us about many different outcomes. It tells us about population density, but it also tells us something about tree cover in this area, about average income, about the road length. And it's the same underlying image that is carrying all of this information and context about this place. So that's the motivation behind my project Mosaics, which stands for multitask, so many different prediction tasks. Observation with satellite imagery and random kitchen sinks is the kind of familiar name of the type of machine learning theory that drives this method. So the idea is we're taking one corpus of global satellite imagery, converting that into a matrix representation. So each location or image is converted into a vector or a row in this matrix. But it's this same pre-computed embedding of the imagery that is useful for predicting forest cover or population density or road networks or many, many other tasks. And so the crucial thing here is this last step is just a linear regression. It's computationally very efficient. And if we compare to traditional neural networks, like here in blue, you see a fine-tuned CNN ResNet 18 network. In general, this much simpler method, Mosaics, is close in performance to this much more complex method. R squared is a metric where higher is better, and we're in general just a few R squared points below. If we put this in context of what it took to actually generate these predictions, each of these green bars to generate predictions on these 7 different tasks took about 2 minutes on a laptop, versus generating a prediction set with a similar amount of accuracy took 8 hours just for a single hyperparameter configuration on what at the time was a pretty large AWS instance with a GPU. So immediately we see differences in who is going to be able to use these technologies, how efficiently maps can be made, how fast and how effectively researchers with different skill sets can say, is satellite imagery a good predictive data for my particular task? It's worth noting that not all unsupervised embeddings like Mosaics will generate a similar performance. In orange, you see a different unsupervised embedding, and you can see that performance is much lower than either Mosaics or the fine-tuned CNN model. But why might we be able to make these algorithmic simplifications that underlie Mosaics and still get similar performance to a deep neural network? Well, many neural networks are actually designed in computer vision, at least for inference on natural imagery. So think anything that you could take a picture of with a camera. So these top two images are both from the very famous ImageNet dataset, and they're both the same class, red panda. And so a model that's going to do well, get high accuracy on ImageNet, needs to be able to distinguish that both of these are red pandas, even though one is a zoomed out picture of the whole body and one is this very zoomed in picture of the red panda's face. If you contrast that with the satellite images on the bottom, they have these specific structures. They're taken roughly from the same distance above the Earth. They're already north-south orthorectified. They're color corrected. So you can see an object in one image, a building or a house in one image roughly is the same scale and extent as in the other. And so these are specific properties of satellite imagery and common to many remotely sensed imagery that help us understand why specific structures in neural nets we might be able to make those a little bit simpler and make those models more efficient. More generally, this is an example of why we need to tailor methods specifically for satellite data. So right now, the general approach is to take innovations that have been made in mainstream machine learning and computer vision, lift them and shift them over, just apply them to satellite imagery almost out of the box, maybe with a few minor modifications. The idea behind my research in the lab, the research we do in the lab, is to really question this paradigm because we can do so much better if we design these models specifically for the characteristics of satellite data. So if this is something that's exciting to you, I would encourage you to read our recent paper from ICML this summer, which really is all about, to the machine learning community, why you need to be thinking differently about satellite imagery versus some of these other image modalities. And one of the most exciting projects that we've done recently is looking at a different type of geospatial machine learning model. And this is a model that, like Mosaics, tries to capture the variation that we have in satellite imagery across the globe. But rather than capture it in an image encoder, by just translating what do we see in the images in all these different places, we also want to train a location encoder, which is a function directly of latitude and longitude. And the contrasting and learning objective, the CLIP objective that we're using here, is borrowed from the CLIP paper from image and text contrastive learning. Now we're doing image and location contrastive learning and saying the output of that function of latitude, longitude, the green function, and the output of the function that takes in the image of those places needs to look similar when the image and the location are from the same place. What this means then is we can end up with a location encoder that functionally looks a lot like what the Mosaics features were doing, that embeds any place on Earth in this high dimensional space. So what that looks like functionally is what you see on the right here. And you can see that the location encoder is learning large scale phenomena like biomes, but is also getting some more fine-grained phenomena in here as well. The particular form of this function f is informed by our desire to actually capture global scale phenomena. And in particular, we wanted to make sure we weren't getting distortion of the poles. So it's built on this paper here, the specific architecture. And much like we could use mosaics features to predict many of those downstream tasks earlier, now we can actually use the direct output of the location encoder as our embeddings for downstream prediction. So what you see on the right here is SatClip generated predictions of ecoregions across the continent of Africa, and in comparison to the true values where every color here is a different ecoregion. And if we compare this with two different location encoders on the bottom, we see that SatClip, which is the upper right map, is getting these, it's kind of the best of both worlds, right? The CSP computing method is overly smooth, whereas the mosaics method, because it actually never incorporates latitude and longitude directionally, is super speckled. But SatClip is able to kind of interpolate between these two in the correct way. So I know we're moving really fast here, but the common thread here is that when we're working with remotely sensed data, we're working with an immense volume of data, and then it becomes very hard to make these models and the machine learning systems actually accessible to the different types of researchers who would want that global information. So both the mosaics and the SatClip projects are about making that global data very accessible, and they do this in different ways. Mosaics does this by pre-computing that feature matrix X ahead of time, and then that is available to many different users. If you go to mosaics.org, you can find how to access those features. StatClip does this by pre-training a model where you can then download the weights and the model in PyTorch and featurize any latitude, longitude point on Earth with that particular model. But coming back to our overall goal here, we want to combine remotely sensed data and geospatial machine learning in order to aid global policy and environmental monitoring. But there's key challenges. We just talked at length about barriers of use and the need to make methods that are more accessible to folks. But we also struggle with the amount and quality of labeled data that is available to train these methods. And as much as we have large corpuses of satellite imagery and other geographic data, often those are going to be imperfect views of the world. So if you think about just the satellite imagery we've been looking at so far, it tells us a lot about a place, but it doesn't tell us everything. So in some sense, that's a weak signal, is the terminology from machine learning. And these questions and these problems of incomplete representation, both in the input space and in the training labels, are not just a problem for geospatial machine learning. These are problems that show up time and time again in general machine learning questions. So when we think about how to approach these types of problems in my lab, it comes down to a question of how does the type of representation that we have in data explain what types of machine learning performance we should be able to expect. And here performance means things like accuracy, but it also means fairness or efficiency. How computationally fast can we run these models? And I want to make this a little bit more concrete with a specific example here. So one thing that we'll see a lot in machine learning generally is that algorithmic systems that perform well on average can still fail significantly in particular subgroups. So in this cartoon, we now have a model. It's trained on some data, and then we make predictions across an entire population. So you can think of the colors as different geographic regions or different demographic groups. But the idea is that this model actually gets pretty low population error on everyone altogether, but most of that low error is coming from the biggest group. And we actually see some pretty poor performance on the blue and teal groups, but because those are such small fractions of the overall population, the average error still looks pretty good. And this is a cartoon version of something that actually happens in the real world. So the gender shade study very famously showed that commercial facial recognition software systems misclassified certain subgroups of the population at much higher rates. In particular, they worked much worse for darker skinned females than other intersectional subgroups. Um, and one very clear reason for this is that those groups were underrepresented in training and evaluation data. So if people aren't familiar with that study, I highly, highly recommend reading the gender shade study. And in fact, the year after that study came out, another paper looked at, well, after all of these companies were kind of called out for this performance gap, what did they do as a result of the gender shade study being published? And somewhat unsurprisingly, those companies went and they tried to balance their training and evaluation data sets, right? They said, we will collect more data and better data from the groups that our model does worse on. But this kind of begs the question, did this whole thing need to happen? Right? Should you have been able to forecast that performance would be really bad on subgroups that you did not have enough or good enough training and evaluation data? And so my collaborators and I asked exactly that question. And we found that underrepresentation of small groups in training data, while it might be a convenient way to sample data, is actually generally inconsistent with optimizing for even an average accuracy objective. And I won't go super deep into the methods here so that we have time for your questions later, but this is kind of what it looks like. If you parameterize groups as different proportions in a population, so think about all these gammas as the actual fraction of each group in that diagram from the very beginning with all the little people icons, then if you're going to design a training data set to maximize performance over all of these folks, you would actually want the groups that have small representation in your population to be oversampled in your training data, because the returns to getting an additional sample for those groups are so big that it outweighs their small part in the overall average, the average accuracy metric that you'll compute. So it's kind of like a mile high view of the type of result that you can get through the methodology that we used in this paper. Another mile high view of what that methodology looks like is we're developing group specific scaling laws. So scaling laws in machine learning are traditionally used to explain how things like the total number of training data points that you have or the model size, how does error decrease as you increase the amount of training data? But group specific scaling laws give us a more nuanced perspective on that. They say if for the blue group, as I get more training data in aggregate and more training data specifically for the blue group, how does that change performance only on the blue group? And we'll do that for the blue group and the teal group, the purple and the yellow. And then because average accuracy is just an average over all of these different colors weighted by their prevalence in the population, we can actually talk about much more nuanced phenomena when it comes to the data set composition, whereas the traditional scaling laws only allow us to talk about the total amount of data, not how that data is composed. Okay. So this is one way of thinking about representation in data is if we have a total training set of size n, what bins does that data come? What demographic groups, what continents? It's a very coarse way to think about numerical representation, but it is still a way that we can operationalize understanding what types of model performance should we expect. So as an example of this, one of the very common things in geospatial machine learning is that it is really costly to go and physically collect samples that we might need for labels. So very often people will not do a uniform at random over space type of sampling, but they will cluster their sample space into distinct spatially clustered areas because you travel once to each cluster and then you sample around those clusters. But this then changes the distribution of our training data, right? So what you see here is a model, a satellite machine learning model. We're looking at performance where higher is better. And as the training set size increases, we get different returns to adding more data for each of these different sampling schemes. But each of these sampling schemes also comes with a significant cost. So the bump from the lowest one to the middle one may not actually be that much of a cost bump to implement, but makes a huge difference in performance. Whereas the bump from this middle red line with a large amount of small clusters to a true uniform at random sample where you would just send people all over the state of Arizona has a smaller accuracy bump, but potentially a much higher cost bump. So these are really practical questions that we can answer with these scaling laws based on the different numerical inclusion type of representation. This also becomes really important for out of sample domain generalization, as we are so often looking at training in one region and then predicting in another. So this question of domain adaptation and domain shift becomes really, really important. But apart from just numerical inclusion, it's important to think of what you actually see in a satellite image. So this is more of a feature representation question. And so what you see here is the main figure from a paper where my collaborators and I looked at satellite-based poverty prediction models from I think this is multispectral satellite imagery. But the idea here is that when you think about predicting something like poverty from satellite imagery, what are actually the visual indicators in the imagery that you would get? And what we found is that most of the performance in predicting relative wealth from satellite imagery could be attributed to just predicting relative levels of infrastructure and urbanization. And so what this means is in many parts of the world, that's a really good proxy for relative wealth. But it means that performance across entire countries that you see in gray here is pretty high, whereas being able to determine relative wealth within only the urban part of the country or only the rural parts of the country ends up being much harder. So this is just an important thing to think about when we think about what types of performance are we actually getting out of our machine learning models, very dependent on the type of representation we have in that input data. In a kind of more constructive view of this, we can actually use that understanding to fuse sorts of data that on their own would not be wholly informative of the outcome that we're trying to predict, but together we can take things like very coarse land cover measurements with very high res, but only a couple classes are represented vector data, and but also specifically model it not as ground truth information, but as this kind of fuzzy prior belief in the Bayesian sense. And then learn from that to get output predictions that are certain, like as you can see with the start colors here, in places where the prior belief and our observation here, satellite imagery, can support disambiguating that uncertainty. But you can see the model remains really uncertain, these kind of fuzzier colors, in places where we're not able to disambiguate what color things should be from the satellite imagery. So here you see these two different light blue colors that are kind of meshed together are different types of wetland. And the model is basically saying, I can tell you from a satellite image what is a road versus a tree, the green and red down here in the lower left, but it's unclear from this image how I should be disambiguating light blue and darker blue wetland. So it's the model is actually capturing and propagating that uncertainty when it should be uncertain. And so all of this kind of goes to an overarching theme of the lab, which is making machine learning more data aware, thinking about the data that's coming in, thinking about what representation do we have, how do we leverage that, even if it's incomplete, and how do we forecast or analyze performance under different data conditions. And so some of this is very theoretical and some of this is very application driven. But the whole point is to kind of go beyond that gray box machine learning algorithm and expand the scope of what we're actually trying to do here. So the two major pillars of the lab are in remote sensing and machine learning and characterizing representation in data. And you can see throughout the slides I've just shown you, there's a lot of interconnection between these two pillars. Since this is a pre-advising session, I also want to note that there is a whole bunch of material and classwork that comes as the foundation to being able to do this type of research. So machine learning and this context or domain-driven machine learning are supported by foundational skills in statistics, optimization, sometimes GIS work, linear algebra, probability, programming, all the way back to calculus. I think you got a sense from the slides of the variety of research we do in the lab, some of it very mathematical and some of it very applied and programming heavy. But these foundations are so important. So if I can give you any pre-advice, it is to take these classes seriously. And with that, I am recruiting PhD students and postdocs this year with interest in statistical and geospatial methodology and context-driven research for real-world problems. Our lab is focused on primarily doing innovative research. A lot of times that's interdisciplinary, but not every project will be. And we are very committed to an environment which is collaborative, supportive, and driven by communication. So if you would like more information on that, you can go to my website, which this is probably a hard color to read. It's just myname.com. And if this is kind of the final slide here, but before I open it up to questions from you all, I think an important question that might be on your minds is, well, what can I get started with right now? And so this is my advice to folks that are thinking about getting into research and especially getting into research at the level of a PhD, which is quite a commitment. Step one is to read. So read research papers in the fields that you're interested in. Read stuff from the last 2 years, read stuff from the last 10 years, read news articles, read blog posts that are made for a different audience than those research papers, read textbooks and see if you want to be learning this foundational material. Really try and get as broad a sense of what is out there as possible. And then after you do some of this reading, Take a step back, pause, and give yourself time to think about not only what interests you, what do you want to be reading about, but what matters to you. Why would this type of research be important to you? What types of things would you hope to learn? What types of impact would you hope to have? And of course, the answer that you come up with now is going to look really different from the answer you have, say, 5 years from now at the end of a PhD, right? And of course, it's going to change, but you're going to be much better off if you have given solid thought to these questions from the outset. And then if you've done all of these things and everything still points to research is a great idea, apply, right? So look specifically for instructions on our applications on our department website, which is linked here. You can see who across the department is recruiting in addition to my lab. You can also get some really great instructions and application tips specifically from that website about how to apply, how to craft personal statements, things like that. And so with that, I think we have a little bit over 20 minutes for Q&A. So if people have questions in the chat, that's great. Or if you want to just unmute yourselves or raise your hands, that's great too. Yeah, Jake, I see a hand.